Hello, so in this video we will talk about the Warshall's algorithm, which is an efficient algorithm to find the transitive closure of a relation R. So just as a recap, if R is a relation on a set A with cardinality n, then the transitive closure of R is given by R star, which is the union from I from 1 to n, R to the I, where our Ri is a composition of R with Ri minus 1. So this is a recursive definition, and we can find r squared, r cube, and up to rn using this definition. Okay, now using matrix representation, if we have r is represented by mr, then r star is represented by mr star, which is equal to mr or mr squared or up to mrn. So note that these are 0 1 matrices here. So we can find the bitwise OR operations for corresponding elements here. And all of them are square matrices because the relation is from A to A. Okay, okay. But this is one method to find the transitive closure. But this is not very efficient. Okay, so an efficient algorithm is the Warshall's algorithm, which we are not going to describe. So the algorithm works like this. The first step is to construct matrices Wk, which is an element is defined by Wij and k. Okay, where Wij k is equal to 1 if a path from vertex I to vertex j exists using only vertices 1 to k as interior vertices. Okay, so what does it mean? It means that if, for example, we have vertices 1, 2, 3 and 4. Okay, so 1, 2, 3 and 4. Then we have, for example, this path, this path and this path. Okay, so this is a path from 1 to 4. Okay, so if we have a matrix here, so this is my 1, 2, 3, 4, 1, 2, 3, 4. So this is my source, this is my destination. So 1 to 4, there is a path exists using 2, 3 and 4. Okay, so therefore we have, if we are trying to find w of 4, then we have 1 to 4 a 1 here. Okay, but if we are trying to find w of 2, then at 1 4 location we have a 0 here, because w of 2 means that we are only allowed to pass through vertices 1 and 2. So vertices 1 and 2 we cannot reach 4. Okay, so now note that this 1 and 4 are starting and ending vertices, so we are only talking about interior vertices. So as interior vertices means they are not starting vertices, and they are not ending vertices, or they are not source, and neither they are destination. Okay, now note that the beauty of this algorithm is that this sentence, if a path from vertex I to vertex j exists using only vertices this as interior vertices, then we have this is equal to 1. This can be written as a recursion. Okay, so this means that if a path from 1 to k exists, this also means that there are two conditions. This it's possible that a path from vertex I to vertex j exists using only 1 to k minus 1 as interior vertices. So one case is that the path already existed using lesser vertices, so automatically it will exist when we introduce more vertices. But there is another option. Another option is that this was not the case. Okay, if this was not the case, then if a path from vertex I to vertex k exists, so remember at the kth step we are introducing the kth vertex as interior vertices. So as a new vertex, a path exists from vertex I to the new vertex, which is vertex k, using only the previous number of vertices, and the new vertex to the destination we can also go using only the previous stories. Okay, so again, our job is to move from I to J using only K's, interior vertices. This is possible that if it was already possible to move from I to J using K minus 1 vertices, this is for sure, because if we can move using only K minus 1 vertices, we can definitely move using K vertices, right? K is not included at all. But if, for example, we could not have done that, then this is also possible that there is a path from vertex I to the new vertex which we introduce here using k minus 1 interior vertices, and from the new vertex to the destination we can move to the using k minus 1 interior vertices again. Okay, so what does this mean? This means that wij k minus 1, this is equal to 1, right? What does this mean? This means wik k minus 1, this is equal to 1. What does this mean? This means wkj k minus 1 is equal to 1. Okay, so our recursion works like this. We say wij, this is equal to wij k minus 1, or wik k minus 1 and wkj k minus 1. So this is what we are trying to get at, and this is the core of Warshall's algorithm. Okay, okay, so let's see an example here. So let's say our A is 1 2 3 4 and our relation is this. Now we have 2 to 1, so therefore we have, this is a digraph representation, so this is digraph representation. Okay, okay, so this is 2 to 1, then 2 to 3, then 3 to 1, and so on. Okay, so you can appreciate that this digraph is actually this one. Okay, now let's start making our matrices here. What is W of 0? W of 0 is just our 1 2 3 4. So W of 0 is just our matrix representation of this relation. So there is uh, no ordered pair in which 1 is the first element, so therefore we have 0 0 0 0 here. For 2 we have 1 and 3 here, so we'll say 1 1 0 and 0. For 3 we have 1 and 4 here, so 1 1 0 0. So 4 we have 1 and 3 again, so 1. So this is my W of 0. Okay, now let's say W of 1. Okay, so for W of 1, remember that, so the ones we have, we just copy them, because the first condition is wij k minus 1, that is equal to, if that is equal to 1, then 1 odd with anything is 1. Okay, now we have to say 1 1. Okay, so there are two ways. You can look at the graph and make it, or you can use the algorithmic equation. So let me write it again here. We have wij k, this is equal to wij k minus 1 odd with wik k minus 1 and wkj k minus 1. Okay, okay, so now this is k is equal to 0, so this is w1, so this means k is equal to 1 here. So we are talking about 1 1 here, so 1 1 0 is 0 here, and then 1, so k is equal to 1 again. 1 1 0 is again 0, and 1 1 0 is 0 here, so this is again 0. Okay, and then you can check that, for example, this is also 0 here. and this is also 0 here, this is also 0, and then we have this is also 0, this is 0, this is 0, this is 0, this is 0, and this is also 0. So it turns out that W1 is same as W0. And why is that? This is because there is no edge here for which 1 is the source. So once we reach 1, we don't have anything anywhere to go. Right? Now we talk about W2. Okay, so we have K is equal to 2, and we are talking about W2. So again, the ones we just copy, and then we have other elements to fill. Okay. Now, can we reach? So can we reach from 1 to 1 using 1 and 2 only? We cannot reach. We can, once we are at 1, we cannot reach anywhere. So then this will be 0 again. Okay. And then we have 0 here, 0 here, 0 here, 0 here. Now let's check this guy. W44. So W442, this is equal to W441, or W42 have 1, and W24. What is W441? This is 0. Or what is W421? So 4 and 2. This is also 0. So, and what is W241? So 2 and 4. This is also 1. 0. Sorry. So this is equal to 0. Therefore, we have write it 0. In other words, looking at this graph, can we reach from 4 to 4 using only 1 and 2? No, because we can go to 1 and then we cannot go to 2 at all. Okay, so we cannot, if we start from 4, we cannot reach 4 back using only these two vertices. Okay, now let's say W3. For W3, I will write some elements which I have already calculated, and then we will talk about one element which actually does change. So we have, let's check this one. Okay. Now this one is W, this is second row and fourth column. So 2, 4 and 3. So what is the formula? W24 2 or W, K is equal to 3, remember? So 2, 3, 2 and W34 2. Okay. What is W24 of 2? So 2 and 4, this is 0. Or what is 2, 3 of 2? So 2 and 3, this is 1. What is 3, 4 of 2? So 1, 2, 3 and 4, this is 1. So this is equal to 0 or 1, this is equal to 1. So therefore we write a 1 here. Okay. Okay. So this one also changes. So why does it change? This changes because from 4 we can use one of these vertex here, one of these vertices here to reach 4 back. So we can go to 3 and then come to 4 back. Okay, so that's why, or you can use this formula again to check it. I mean, for small matrices, this method is easy, just looking at the graph and use inspection. But imagine you have a huge graph and you want the computer to do it. So this algorithm is actually making our lives very easy. Complexity wise. Okay, now similarly W4, this is equal to, we'll again do one such element which does change its condition. So 1 0 1 1 and then 1 0, and then actually you can appreciate that this does change, but for the sake of completion we will do it. So this is what, 3 3. So W 3 3 and 4. So this is equal to W 3 3 of 3 or W34 of 3 and W43 of 3. So this guy is 0, this guy is 1, and this guy is 1. Why? W33 of 3 is 0, W434 is 1, and W43 is also 1. So this and this is 1, and 1 or 0 is 1. So therefore we have a 1 here. So this is our transitive of our R. Okay, so when we reach Wn, okay, so let's go here. Wn, this is equal to transitive closure. Okay, closure. Or we can say Wn, this is equal to Mr star. Okay, so in other words, Wn contain all the possible paths from the original graph, okay, which is the same as Mr star. Okay, so just for completion, the complexity is of the order of n cube. Why ORing all matrices is of the order of approximately n to the 4. Okay, okay, so this is a small demonstration of how the Warshall's algorithm works. Okay, so if we want to write a pseudocode of that, so we'll say for k is equal to 1 to n, for I is equal to 1 to n, for j is equal to 1 to n, wij k, this is equal to wij k minus 1, or wik k minus 1, and wkj k minus 1. Straightforward, right? And then this ends, this ends, and this ends. We start with w of 0 and our ends wij k. These form our wk, which is an output. Okay, or k, or you can say n actually. Okay, okay, so this is very easy to program the algorithm. So if you have a relation and you have a matrix representation, it is straightforward to plug that relation into the program, and it will give you the transitive closure of the relation. So this is it about the Warshall's algorithm and its example. Hope it was easy to understand, and thanks for watching. Hope you liked the video.